Hello, everybody, and welcome to another wonderful day of chemistry. So today we're going to be talking about how multiple electrons essentially interact within a given system. And for that, we're going to have to use a little bit more of kind of some upper level physics. So when we're talking about how electrons interact, the first important thing is that electrons are negatively charged particles, and as such, they tend to repulse each other. However, whenever we have atoms with multiple electrons, they can also interact through another force. And this actually has a large part to do with the fact that that they have an additional quantum number. And this was originally discovered using neutral atoms, specifically silver. And what was observed is that if you shot these neutral silver atoms through a magnetic field, they could actually be deflected through the magnetic field. And this is really awkward because if you take a look at your periodic table, silver is just above gold in the periodic table. Gold isn't typically magnetic. So the question was why? And the reason why is that they were individual silver atoms. And individual silver atoms, like individual gold atoms, have a single unpaired electron. So they have a single electron that can be affected through the magnetic field by magnetic fields in a very discrete way. Because when you shot these atoms through their magnetic field, they'd either go up or down. They would never go straight. So they have two options. So all of these magnetic fields generate some sort of magnetic field that interacts with the imposed magnetic field. And it was observed that the reason why is that it turns out that electrons are essentially a negatively charged particle that spins. And it turns out that a moving charged particle can generate a magnetic field. So typically we think of this as you can have a mild magnetic field generated by things like photons as they travel through a straight line. And we saw this with electromagnetic radiation. However, if you move a charged particle in a circular pattern, you can generate, say, a magnetic force like you find with electromagnets. Well, it turns out that electrons do this on a very minor scale. So think of it like a baseball. As it spins around and round, it generates this additional force. In the electron's case, that's a magnetic field. And it turns out that this magnetic field can be pointed in one of two directions, because either they can be spinning clockwise and generating a magnetic field pointed up, or they can be spinning counterclockwise and generate a magnetic field pointed down. So this generates one last quantum number called the magnetic spin quantum number. Usually, unless you're in an upper level physics class, this is usually referred to as spin. So it can be up, which we represent with an m sub s value of +1/2, or down with an m sub s value of -1/2. Now, a very cool thing is that it doesn't matter what the n, l, or m sub l values are. The m sub s, or spin, either is one of these two values, up or down, and that's it. And this is purely based on the direction of the magnetic field. Now, a very cool feature that was discovered about these spinning electrons is that it turns out that if electrons have the same spin, they always stay apart. So if I've got two electrons spinning up, they tend to push away from each other, and this generates less electronic repulsion, because if you can't get as close to each other, you don't notice how much the other person smells, so it's not that big of a deal. However, if electrons have opposite spins, they can get a little bit closer together and can generate greater electronic repulsions. And we're going to see that this becomes very important later on. But one of the first important consequences of this spin quantum number is it turns out that any quantum particle that can spin, like an electron or a neutron or a proton, can't possess the exact same quantum numbers. So in the electron's case, we have 4 quantum numbers, and they can never be quite identical. At least one of them has to change, which means that if I'm looking at electrons with quantum numbers n, l, and m sub l, I can have two electrons with these same exact values, one with the spin up and one with the spin down. And this actually has some really cool implications of how many electrons can fit in a given shell or subshell. So if I'm looking at the s subshell, also called the s orbital, because we only have one for a given n value, it can only contain two electrons, one up, one down. So any s orbital, no matter which one it is, no matter the n value, only has two electrons. Any p subshell can only contain 6 electrons because I have 3 separate orbitals, -1, 0, and +1, and each one can only contain 1 electron, up or down. So this gives us 6 electrons in the p subshell. If I look at the d subshell, this generates 5 orbitals and 10 electrons, 1 in each one, whether it's up or down. And this actually has some really important consequences when I start putting multiple electrons around an atom, because as each subshell can only contain a set number of electrons, that means as I get more electrons, they have to move into a different subshell or a different energy level. And all of this is complicated by the fact that the energies of each of these subshells will change as more electrons enter the atom. So next time, we're going to be talking about the Aufbau principle, or more or less, what's the electron configuration of any given atom? Until then, take care.